Bismillahirrahmanirrahim. I am Professor Jamil and you are watching my YouTube channel. Today we are going to have a lecture on Cauchy-Riemann equations, which is an important article in the theory of complex variables or complex analysis. These equations uh, check whether a given complex function is analytic or not. Analytic means differentiable, and these Cauchy-Riemann equations may be asked you in your exam in the form of a question whose statement could be this one. Let's check. Remember, the Cauchy-Riemann conditions, these are in fact partial differential equations of first order, and these equations may be written in any coordinate system, whichever you choose. And for the time being, the coordinate system I have selected for you is the Cartesian coordinate system. Later, we shall also derive Cauchy-Riemann conditions for the case of polar coordinate system. So let's start in the form of a question, the Cauchy-Riemann conditions or Cauchy-Riemann equations. So first of all, there is a heading for you, Cauchy-Riemann equations in Cartesian coordinate system, and the question may appear in the form of a statement like this. Prove using Cartesian coordinate system, mean x and y coordinate system, that Cauchy-Riemann equations are the necessary and sufficient conditions for analytic complex function. Analytic complex function mean a function which depends on the complex variable z, and this function is a differentiable function. From the word analytic, it means the function is differentiable. Now, necessary condition means what? And sufficient conditions mean what? These can be explained in the form of another statement for the question. Look, the complex function fz, this is analytic. You are given that the complex function fz, in which real part is u, which is a function of x and y. X and y are real variables, so this u is a real function. V is also a function of x and y, and x and y are the real variables, and v is a real function. And you have been told that this is analytic. What are you asked? Prove that u and v, mean this u and this v, are such, mean this u and v are such functions that these conditions are satisfied. These are known as Cauchy-Riemann conditions. Mean what? You are given that function is analytic, and you have been asked proof that this u and v, which are real part and imaginary part of the complex function, they satisfy these conditions. So this is what we mean from the necessary conditions. So necessity is, if the function is analytic, then these conditions must be satisfied. There is another part of this question. Establish its converse as well. We have to establish the converse of its, mean this statement. What will be converse? Mean read the sentence in the opposite direction. Mean you are given these conditions, and from these conditions you have to prove that the function is analytic, mean function is differentiable. Okay, and this is what is meant from the word sufficient condition. Sufficient condition means if the Cauchy-Riemann conditions are satisfied, then function will be differentiable, mean function will be analytic. So this means in sufficient condition, and these first two lines mean necessary conditions. Let's prove these conditions, and we make a proof on another board. Proof. Necessary condition will be proved first, and in that condition, what is given? Given is that fz equal u, which is a function of x and y, this is a real function, plus iota into v. V is a function of x and y. So given this, fz is analytic. And now we have to prove the Cauchy-Riemann conditions, right? So what is implied from this line? This implies fz is differentiable. And what this line means, derivative of this function, the derivative will be taken with respect to z, because f depends on the z variable, independent variable is z. So this, when you said fz is differentiable, this means this derivative is in fact a limit. Delta z approaches to 0, delta f of z divided by delta z is unique and finite. So when you say that the function is differentiable, it means this derivative, which is in the form of a limit, is unique and finite. What does it mean from the word unique? Unique means however or in which way you evaluate this limit, the answer for this ratio will always be same. Now understand, this z contains two variables, x and y, means z is equal to x plus iota y. So there are two variables. One variable is x, which means x-axis, and other variable is y, which means y-axis. So you can evaluate this limit either along x-axis or along y-axis. So, and evaluating this limit along x-axis means taking the derivative along x-axis. And evaluating this limit for y-axis would mean that this derivative is to be evaluated along y-axis. And now, whether you take derivative, mean evaluate this limit along x-axis, or whether you evaluate this limit, mean this derivative, along y-axis, the answer will be same. This is what is meant from the word unique. And finite, you understand, means this value is not infinite. This is a finite value. And similarly, this one is infinite. Now, when you evaluate this derivative along x-axis, mean x will be the variable. And what will be delta y? Delta y will be 0. So this implies delta y is 0. Along y-axis means y will be the variable and x will be constant. And when x is constant, that means delta x is 0. So along y-axis means delta x is 0, and along x-axis means delta y is 0. This is a very unique way of deriving the Cauchy-Riemann conditions. This is not usually done in the books. So be careful and learn very carefully. Let's evaluate this derivative. d by dz of fz, and fz is what? This u plus I v. Now we understand that u is a function of x and y, and v is also a function of x and y. You do not need to write these arguments x and y again and again in front of after u or after v. Okay, and when you evaluate this, then this means y is a constant, and this means d by dz of fz, and fz is same again, u plus I v, and when you will evaluate this derivative, then x will be constant. Now, u is a function of x and y. Let's apply this. You need to find the d by dz of u plus I is a constant, so it can be written outside d by dz, and you have d by dz of v. and for these y is a constant. Similarly, on the right hand side, you have d by dz of u plus iota d by dz of v, and when you evaluate this, then x will be equal to some constant. Right? Now, let's move on the other board. In fact, I should write these derivatives. Okay. Now, look, d by dz is to be taken of u, but u is a function of x and y, which means you will need to apply the chain rule of differentiation. Mean you will differentiate first u with respect to x, then with respect to z. Let's apply this rule. So this is derivative of u with respect to x, and then x will be differentiated with respect to z. Right? This. But u also contains y, but y is a constant. So derivative of u with respect to y will be 0. So here is 0. Derivative of u with respect to y will be 0, multiplied by anything will be 0. Okay. So this derivative has been done, plus iota and you need to differentiate v with respect to z, but v is a function of x and y. So when you differentiate with respect to z, you will differentiate v first with respect to x, because x is your variable, y is constant. Remember this point. So you will differentiate v with respect to x, and then x will be differentiated with respect to z, mean chain rule of differentiation. So derivative of v with respect to x, and then x is to be differentiated with respect to z. But v is also a function of y, but y is constant. So derivative of v with respect to y will be again 0. Mean when you say y is constant, it means v does not change with respect to y. Mean v is a constant with respect to y. When argument does not change, then the function does not change. So when y is constant, then y is not changing, it means v is not changing with respect to y. Mean partial v over partial y is 0. So the second term here will be 0. Right? So this derivative has been done. And why the partial derivative? Because u has two variables x and y, and you are differentiating with respect to x first, and x will be differentiated with respect to z then, because you have to take derivative in fact with respect to z. So you need first to differentiate u with respect to x, then with respect to z. Let's do on the right hand side. Equal to this. You need to differentiate u with respect to z, and you will differentiate as you have done on the left, but this time x is constant. Remember this point. So u contains two variables x and y. You will differentiate u with respect to x and then with respect to y, but x is a constant, so derivative of u with respect to x will be 0. So in the first place you will write 0 plus derivative of u with respect to y, and then derivative of y with respect to z. Okay, so this has been done. Please make a parenthesis on it, mean round bracket, and plus iota d by dz of v. Listen again, v is again a function of x and y. So you will differentiate v first with respect to x and then with respect to z. But x is a constant. So derivative of v with respect to x will be 0. So here again you have plus iota into 0 plus, this was derivative with respect to x, and then you will take derivative of v with respect to y, and that will be partial v over partial y, because v contains two variables x and y. That is why we are using the partial derivatives. So derivative of v with respect to y, and then y will be differentiated with respect to z, right? So this was the du by dz and the rest of the derivatives. Let's now simplify. Now you need derivative of x with respect to z, and here, and derivative of y with respect to z. But you know z is equal to x plus iota y. Now you need to take partial x over partial z. So differentiate this. Look, partial over partial z of z. Here you have partial over partial z of x plus iota partial over z of y. Right? But this number is 1 and this is partial x by partial z plus, when you evaluate x over z in the left hand side, your y is constant. When y is constant, then derivative of y with respect to z will also be constant for the left case, right? You can write it for y equal to constant, and so you have partial x over z as equal to 1, and when you evaluate this side, here y is constant, x is constant. Look, this x is constant, and when x is constant, then partial x over partial z will be constant. So on left hand side you have 1, because partial z by partial z is a unity, 1. It looks as if they will be cancelling to produce 1. On the right hand side you have 0 plus I, and derivative of y with respect to z is the same as before, and this is equal to 1 equal to iota partial y over z, and partial y over z is equal to 1 over I, and this means partial y over z is equal to minus I. 1 over I is minus I, and make a box and use these in your equation number 1, for example. These calculations are very important. In this side, you on the left hand side, you have y constant, and if you like, you will write as y equal to constant and y equal to constant. And on the right hand side, you have x constant. So you can write x constant and x equal to constant. And now you understand, when you need to evaluate partial x over z, then you will use y constant, and that y constant will produce derivative of constant with respect to z will be 0, and so partial x over partial z is 1. Similarly, for this piece you need partial y over partial z, and your x is constant, and when you use this x constant here, then derivative of constant with respect to z will be again 0, and here you have 0, and 0 plus something is this, and I will be coming down, and you will have minus I. Now use these two equations, you can name them equation number 2 and equation number 3. Use these equation 2 and 3 in your equation 1. So using equations 2 and 3 in equation 1, we get what you get. Let's write in the downside, in this side in fact. So let's apply partial u by x into partial x by z is 1 plus 0 and plus I, and partial v by x into partial x by z. Here is your partial x by z, again 1, and plus 0 equal to, now on the right hand side you have 0 plus partial u by y, and y over z. Here is y over z, it is minus I. So you have minus I plus I for iota, 0 plus partial v over y, and you have partial y over z. This is minus I again, and here is your minus I again. Now simplify. Multiply by 1, it will give you u by x plus I partial v by x equal, this is minus partial u by y, and then multiply I with I will make minus 1, and multiply this minus 1 will make plus 1. So you have plus, here you have I, minus sign and I, and this will give you plus partial v over y. Look, this minus here and I on the right, and this iota multiply with iota is minus 1, and this minus 1 will make plus 1. So it is partial v over y. Now you have on the left hand side, you have something plus iota into something. This is a complex number, and similarly you have on the right hand side complex number. This is the real part, this is the real part, and when two complex numbers are same, then the real parts will be equal to real part, and similarly coefficient of iota mean this thing, this is known as imaginary part, and here the coefficient of iota is this, right? So whatever imaginary part is on left, that will be same as imaginary part on right. So let's equating the real and imaginary parts. So what you get, partial u by x equal, this is the real part, means something without iota, and the real part on right hand side is partial v over y, and the other thing is coefficient of iota is partial v by x, and it is equal to, coefficient of iota is this, minus partial u by y. So these are the conditions. Let's check. These are same as you were asked in your statement, right? Let me check the statement. Yes, u by x equal to v over y. This is u by x equal to v over y, and the other one is u over y equal minus v by x. U over y, here you have u over y, and minus v by x, you can take minus sign here. So according to the statement, you can write these two as partial u by x equal partial v by y, and partial u by y is this on the left and left side on the right, minus partial v over x. So these are the Cauchy-Riemann conditions or Cauchy-Riemann equations. So now you understand that when a function is analytic, here we started from here, the function is analytic, and this definition means differentiable, and from this word we have gone through a series of steps. The series of steps is this. From this you were here, and you have ended up with a set of two equations which are known as Cauchy-Riemann equations. So this is first part of the proof. Now we have to do the converse, and converse is what? You will assume that these conditions are satisfied by the real and imaginary parts of some complex function. Then from these conditions you will prove that the function is differentiable, mean df by dz is unique and finite. This is to be proved now. So let's do the converse. Let's do the converse. And let's do the converse here. Conversely, let the Cauchy-Riemann, C for Cauchy, R for Riemann, and equations. What are the equations? You write again, u by x equal partial v by y, and partial u by y equal minus partial v by x. These are the Cauchy-Riemann conditions. So conversely, let the Cauchy-Riemann conditions are satisfied by the real and imaginary parts of complex function fz equal to u, which is the function of x and y, plus iota v, which is the function of x and y. Now you have assumed that these Cauchy-Riemann conditions are satisfied by the real and imaginary parts of the complex function, this fz, and this u is the real part of fz, and coefficient of iota, remember, not iota, coefficient of iota, mean whatever is multiplied with plus iota here, that v, and this v is known as imaginary part of the complex function fz. So, and we have to prove now that this function fz is differentiable, mean its derivative, which is a limit, that will be unique and finite. So let's start its proof. And how can you go along? From these you can write these two as equation number 4 and then equation number 5, because we have numbered our equations up to 3 already, and the next number is 4 and 5. You need to make a derivative of this something, and for this case let us write CR equations as partial u by x equal v over y, and the derivative with respect to x is to be shifted on left, mean partial v over x is equal to minus u over y. Why I have done this? On the left you have partial over partial x, and on the right hand side you have partial over partial y in both equations. And from this you can develop a complex number. How you can develop a complex number? If this is your equation number 6, this is your equation number 7, and you can produce a complex number from these two, because your function is in this form, u plus iv, and mean this is some real function and this is also some real function, but it is obtained from the derivative of u. So this is equation number 6. Look, equation number 6 plus iota multiply with equation number 7 implies, what does it implies? This thing, u by x plus iota into v by x, and on the right do the same, partial v over y, and iota multiplied will produce a minus sign, minus partial u by y, and from here you can take partial over partial x common, and u plus iv is within the brackets, and on the right hand side you have partial over partial y and v minus iota u. Now u plus iv, this is your fz, but on the right hand side you do not have u plus iv, so you can take I common, mean you can pull out I, and what you will get, keep left as before, mean u plus iv, and from here partial over partial by, you can also say that you have divided and multiplied with u, so that coefficient of u, which is now I, it vanishes from here. And how it vanishes? Look, I scale will be minus 1 and this will make plus 1. So partial over x u plus iv equal partial over y. 1 over I is minus I, and this is iv and plus u. This minus I can be taken out, and you have partial over x into u plus iv equal minus I, and partial over y into this u can be, this can be written as u plus iv, because addition is commutative. U can be written first and iv can be written afterwards. Now what is this? Look, this is partial over x, and u plus iv is your fz, and here minus I partial over y, and this is again fz. Now look at this thing, partial over partial x, you need part d by dz, because you need to prove that fz is differentiable. When you say fz is differentiable, it means derivative of fz is to be taken with respect to z. And how can we get it? Use chain rule of differentiation here again. So here is your chain rule of differentiation. Partial over z fz and derivative of z with respect to x. Partial z will cancel and you will get partial over partial x here. Use this very same rule, mean chain rule of differentiation on right hand side, minus I partial over z of fz and then derivative of z with respect to x, right? Now you need to find derivative of z with respect to x and derivative of z with respect to y. and this is the derivative with respect to x. It means on the left hand side your y is constant, and this is the derivative with respect to y. That means your x is constant here, because partial over partial x means you are differentiating the function with respect to x only, which means y is to be taken as constant. So as z is x plus iota y, then look for here. On the left hand side your y is constant. So derivative of z is to be taken with respect to x. Let's write it. Partial over z fz into derivative of z with respect to x. Z with respect to x mean x, derivative of x with respect to x, that is 1, because y is constant on left, and on the right you have minus I and partial over z fz, and on the right hand side you need to differentiate z with respect to y, but for this case on the right hand side x is a constant. So when x is constant, and the derivative of x with respect to y will be 0, and derivative of z with respect to y would mean iota into partial y over partial y, that will be 1. In fact, you can write from here as well. Partial z by x is 1 because y is constant on the left hand side, and partial z by y, this is for the right hand side where x is constant, and when you differentiate z with respect to y, x constant, that means derivative is 0, and this I is constant, it will be left as such, and derivative of y with respect to y will be 1. So on the right hand side partial z over y is I, and on the left hand side partial z by x mean this is 1. Now your fz, now f is a function of z and you are taking derivative with respect to z. Since your function f depends on one variable, and in this case the partial sign can be converted into the total derivatives. So or this is d by dz of fz, and this is for the case when y is constant, equal to this I into I will make I square, that is minus 1, and this minus 1 will make it plus 1, and partial is to be now converted to total derivative because f now depends on one variable, and differentiation of one variable is usually written with d by d. So it is fz, and for the right hand side your x is constant. And what does it mean? D by dz fz, and y is constant, mean x is variable, mean this derivative is to be calculated along x-axis, mean this derivative is to be evaluated in the x direction, and on the right hand side df by dz, and x equal to constant mean your variable is y and y is along y-axis. So this is the derivative which is to be taken along y-axis. And look, derivative of fz along x-axis is equal to derivative of fz along y-axis. This means d by dz fz is unique, and it is of course finite and finite, because infinity cannot be equal to infinity. This is very important. On the left hand side infinity may mean something else, and on the right hand side infinity may mean something else, but these are same. Since there is an equality sign, it means certainly the left hand side is finite and the right hand side is finite. That's why I have written d by dz of fz is unique and finite, and this means what? Fz is differentiable. This is what we were intending to prove. You were given the Cauchy-Riemann conditions, and from the Cauchy-Riemann conditions we have proved that fz is differentiable, right? So you understand, if you are given fz is differentiable, then function will be analytic. Sorry. If you are given that fz is analytic, then the Cauchy-Riemann conditions will be satisfied. This is what we mean from the necessary condition. And what is the sufficient condition? That means if the Cauchy-Riemann conditions are satisfied, then the function fz, complex function fz, will be differentiable, mean analytic. This fz is differentiable, mean you can write one more sentence, one more line. This means fz differentiable. This means you can write or fz is analytic. And this completes our proof. This is your answer. And you can write a short statement for it. Hence, Cauchy-Riemann conditions are the necessary and sufficient, S for sufficient and for necessary and sufficient conditions for a complex function to be analytic. And your question is finished. This is your final answer. I hope this proof of the Cauchy-Riemann equations, or this derivation of the Cauchy-Riemann equations, should be useful to you, and please understand these lines, mean the steps in this derivation very carefully. These are simple differentiation you need to use for the complex function, and it should be of some value to you, and I hope you will practice it at least 3 times when you have learned all the steps here. Thanks for watching. Keep watching for more interesting proofs and derivations and questions on complex variable. Please subscribe, share, and press the bell icon so that my every lecture reaches you in the first place. Thanks for watching.